Hi, biochemistry students. Okay, hey, we're going to switch our attention from solutions to gases. And so let's take a look here at some of these ideas. There's an ideal gas law that combines pressure, temperature, volume, and moles. And so we're familiar with moles because moles is tied to mass, but this time we're relating that to gases. Gases like oxygen gas, nitrogen gas, chlorine gas, hydrogen gas, those kind of things. Now, there is a principle about gases called Boyle's law that makes sense. It's the equation is pressure, the first pressure times the second volume, or excuse me, the first volume equals the second pressure times the second volume. So the relationship is like if the pressure changes, the volume would change. And so that's, you'd think of the conditions before this happens and then the conditions after. So it's pretty simple. If you think about it, if you pressed on a gas, you could decrease its volume. And so that's commonly done. That's Boyle's law. And you could think of that as an inverse relationship. When one goes up, the other goes down, and vice versa. Okay, so that's Boyle's law. Here's a diagram for that. Put pressure on something, volume decreases. Now here's Charles' law. Charles' law is the opposite of that. They're directly proportional. So like if you had a gas in a container that allowed the gas to expand, and you increase the temperature, you would expect that gas to expand. We've probably all experienced that in some way, but it makes sense now that you increase temperature and then the volume would increase, or vice versa. And so this is what we would call a directly proportional relationship. Okay, so there's Charles' law, there's Boyle's law, and again, here is the idea. So if you just had a container that gas could be expanded, you would expect it to increase in volume if the temperature was increased. Now, Avogadro had some other ideas too, being a historical figure in chemistry. But Avogadro basically says that if a gas volume increased, so would the amount of moles. And so he was thinking in terms of accounting for how many molecules and things like that. So that's, again, a direct proportional relationship. Okay, so you can think of a balloon. If you had 1 mole of oxygen gas, you would expect the volume to be such. And then if the volume did increase, then in order to do that for that particular temperature, you would have a larger space. Volume would increase, and the number of moles would have to be related to that. So now the ideal gas law, which is what we're going to be working with here this week, brings all those things together. Okay, so what does it look like? So P is pressure, V is volume, N is the number of moles. Now we've learned how to calculate moles, so that shouldn't be a problem. We're introducing something here called the gas constant. This is a number that doesn't change, so you'll have this set number that you can work with. And then temperature. Now temperature, remember, is either measured in Fahrenheit or Celsius, but what we'll have to do is take the Celsius degree and convert it to Kelvin. Now you do that by adding 273 every time. So whatever the Celsius degree value is, you add 273, and that's the Kelvin degree. Okay, so here's a breakdown of that. Here's the value we'd always use for R. That's our gas constant. Okay, so here's a problem here that solves for pressure. And as we look down through here, it shows how to solve that. Now this problem here solves for volume, so you can see that that's going to be your challenge here. And then here's one that solves for volume again. Okay, so thanks for watching, and I'll be making some examples, and I'll be posting those in our modules. Talk to you later.